Okay, so welcome back, everybody. And to start with, first of all, I just wanted to ask you if you have any questions left from the previous lecture. Just raise your hand or put it in the chat. I think now I can see the chat. Otherwise, what I would like to do is, because we are now, the next thing we are going to do is to look at matching algorithms and how to implement it efficiently. So I would like to start with a little recap, just so that we remember what we are trying to do. So we have this nominal language, we have the syntax of nominal terms, which is just like first order terms, but with an abstraction construct, which we use this syntax with the square brackets to say which atom we are abstracting. And the other difference with respect to first order syntax is we can suspend the permutation on a variable. And then the problem we have is that we want to implement efficiently. So we have an alpha equivalence relation axiomatized on these terms and a freshness relation. And we know how to check alpha equality or freshness by simplification, by applying these simplification rules as much as possible. But the question is, can we implement this efficiently? Because, for example, we know that it's very efficient to do this sort of operations with first order terms. It's one of the keys to the success of functional programming and logic programming, that we can match and unify terms efficiently. So now we have terms modulo alpha. What is the extra cost for matching and unification? So we want to do it efficiently. So the places where we need to look for potential problems that we need to address to get efficiency is the management of permutations. So these simplification rules, for example, this one and this one, the one for abstractions generates here a permutation that needs to be applied, a swapping that needs to be applied to L. Now, AB act L itself is not a term. This is a notation to say apply the swapping AB to the term L. So here we need to think a little bit, because if each time we apply this rule, we do apply this swapping to L, there will be a cost, because to apply the swapping to L, we need to traverse the term L, finding any occurrences of A or B in the tree to swap them. So if we implement this in an eager way, I mean, each time we apply a rule, we really apply the swapping, we will not be able to get the same. So we know that matching and unification in first order terms, the best algorithms are linear. So, and they are linear because they cleverly use structures that share variables, for example. So we are going to try to use the same trick here, but in addition, we need to worry about, as I said, how do we implement these permutations? And we know that if we want to keep linear time efficiency, linear time algorithms, we can't apply the swapping eagerly. So first thing we are going to try to do is to manage the permutations in a lazy way, which means that we will let them accumulate on terms. So that's one thing. The other thing is, when and how do we test for freshness of an atom? Because again, if we do this eagerly, each time we apply this rule, we need to check for freshness of A in L, which will imply traversing L. You know, the rules that implement freshness go over the syntax of the term. So this is a potential place where we can also move to a nonlinear time complexity. So with these things in mind, we are going to try to define the matching algorithm. So let me go back to where we were. That was just a recap and just pointing out the places where we need to be careful to get an efficient implementation. So to get a polynomial implementation, we will need to do sharing of variables as it's done with first order unification algorithms. And we will need to apply permutations lazily, so push them down a term only when needed. But we also need to be we need to think a little bit about how we represent those permutations, because the rules generate these permutations that will accumulate. So potentially we will end up with a big list of swappings. So is there a better way of representing these permutations? And actually, so the algorithm I'm going to describe is a linear time matching alpha equivalence check and matching algorithm that was designed by Christophe Calvez in his PhD thesis, which uses a representation of permutations in what he called an environment. And an environment is a compact representation of a permutation and a set of atoms that will need to check for freshness. So remember, we are going to apply permutations lazily and check freshness lazily. So we will keep this structure of a permutation and a set of atoms. And the permutation will be represented either with, because a permutation is a bijection with a finite domain, so we need some way of representing this map. So we can imagine for the moment that we have some kind of array or functional map, okay? So we represent our problem, our matching problem, as a term S and a term T with potentially a permutation and a set of freshness constraints that will need checking. So an environment problem will be just a list of those equality problems. And so we will represent our matching problem in this way, at the beginning just with it and an empty set of atoms. But these things will grow as the algorithm applies. And the algorithm will apply simplification rules, taking into account that each time a permutation is generated, it needs to be added in this environment. Each time freshness constraints are generated, it need to be added in the environment. And so we'll do these phases of simplifying our environment constraints. Once we reach the end of the simplification of the constraints, we try to deal with the permutations and the freshness, and that will produce some like normal form or standard form of a problem from which we will try to find the solutions. So the core algorithm, the idea is to try to transform our problem into a format from which we can directly derive the solutions. So I'm not going to go in detail into the rules. The idea is similar to what I explained before. These are simplification rules. So the goal is given a problem. So a problem, as I said, is a set of these kinds of equality constraints, term and term with environment. And given a problem, so a set of those things, we apply these transformation rules with the goal of simplify as much as possible. The rules are syntax directed. So you look at the form of your term and you check which rule to apply, like the simplification rules I mentioned before. And at each point, you might already detect a failure, or you might be able to proceed. So for example, if you're trying to match or check an equality and you have F as a term former at the root here, you know that this one has to have an F also at the root. And if not, you already know the equality check will fail. Okay, so the rules can either proceed with the simplification or will detect a failure, and there you can stop. And if all goes well, so these rules terminate. You can easily prove that they terminate. As I said, they go over the syntax of the term and they go down the term, simplifying the problem. So you can check that after you apply exhaustively these rules, either you found a failure and that's it, or you simplify sufficiently your expressions so that you end up with constraints that have a format, specific format, where you have a variable on one side and a term on the other with an environment. So that's the first simplification phase. And we went just once over the terms. Okay, so for the moment, this is still linear complexity. for pinning terms. I'm just looking at the chat. Yeah, no, it doesn't. There's a question in the chat about how do you look at the terms. So they are syntax-directed rules, and basically they are looking. Here I put like cases. I made cases on the left because this to me represents the pattern that I'm trying to match, or just two terms that I want to check for equality. So because the problem is there's a kind of symmetry here, because for example, you see if this is an A, the only way it will be equal here is I have to have something like an atom on this side. It's just easier to specify the algorithm with cases here because I have the environment on this side, which makes things more complicated. But the algorithm just basically is a traversal of the tree. So this is just about, sorry, the question was about the position of the PR. No, the position of the PR, this is completely irrelevant because it's a set here. So I'm actually a multi-set. So we're working with lists of these constraints, and the order doesn't really matter. The rules apply basically non-deterministically over the problem, trying to simplify as much as possible. Okay, so you apply your rules wherever, if in the list input problem there is anything of this type, you can apply this rule, but obviously you might be able to apply different rules in different parts of the problem. You just do it in any order. Okay, so we apply this, we simplified our problems. Now we have these kind of problems to deal with. And what we do is in the second phase of the algorithm, we try to look at what kind of thing X needs to be. Okay, so what this rule is doing, similar to the simplification rule I mentioned first, when I first explained the alpha equality checks, is that the permutation that is here waiting on the X, we can move it to the other side with a pi minus 1. And remember that this environment here is what holds the permutations. So what we need to do is to let the environment know that we've got pi minus 1 there. So what this means is that we need an efficient way to know what the inverse of a permutation is, and an efficient way of linking these permutations. So for this is what I was telling you before. We need a data structure that allows us very quickly to find the image of an atom and the inverse. So if we're using, for example, an array, since the permutations have a finite domain, we can have a finite array to specify the mappings. And in this way, we can quickly find pi of A and do the inverse. So the phase 2 applies this rule, again, exhaustively. So we end up with constraints that have just a variable on the left. So we are almost there. The next phase propagates the environment, because this environment, remember, is a permutation and a set of atoms that we need to check for freshness. So we need to look at the term we have here. And if, for example, here it said that A needs to be fresh, then this is a problem because A is not fresh in this case. So that can give failure. So these rules, again, could fail or could work properly, in which case, at the end of this phase, we have simplified the problem so that we get either bottom representing failure or something that looks like a substitution, where these terms here still are not exactly the terms we want. They are not exactly nominal terms, but they are almost, because we propagated with these rules the environment to the leaves. So where there is a variable in the term, we might have still that environment left there, but for all the rest of the term, we pushed it down. So at this point, again, we've just moved through the terms, so there's still linear complexity. We haven't needed any second pass, but we are, as I said, almost there. We still haven't got really the answer. what we will do next is a simple rewriting of this term to put it in the format that we like, which is a substitution of x with a nominal term and freshness constraints of the form atom and variable. So we read the environment, and the environment contains the permutation and the set of atoms that need to be fresh. So we simply split that. We leave the permutation decorating the variable, suspended next to the variable, and just put the atoms as freshness constraints. So it's 4 phases. This last one, if you like, is just like a pretty printing just to output things in the format we want. But the key thing is, first of all, that the rules are terminating, so they're always actually simplifying. They preserve the set of solutions, so what we get at the end, if it didn't fail, we get the solution of the problem. And we can check not only alpha equivalence. If we just want alpha equivalence, we run the core algorithm, but if we want sorry, I forgot to mention something. Remember that the normal forms are x equals t. I told you they look like a substitution already. There is a little issue here, which is that this term t, if we are really looking for alpha equality, if the term t is not ground, it could contain x itself. And we need to be careful because we could even have problems where the variable x occurs many times. So nonlinear terms might create problems with x many times. So this x here could occur in other equality constraints within PR. So when we are solving the problem, once we reach this and we know that x has to be equal to t, we need to be careful with what happens also here. So if t is pi x and the support of pi is fresh for x, we finished. But if t is something else, it could be a term that contains x inside, it could be some other thing, and we are checking just for alpha equivalence, then we have a problem. So if we need to now know at this point, are we just checking for alpha equivalence or are we matching? If we are just checking for alpha equivalence, then this is what we need to check, that t is pi x and pi is fresh for x. This support of pi means the atoms that pi modifies are fresh for x. So that's if we are checking for alpha equivalence. But if we are going to match, we need to do more work because, as I say, this x could occur inside PR, so we need to continue processing the problem. So at this point, the algorithm, so we have a core algorithm, but the core algorithm will need to do different things now depending whether we are checking alpha equivalence or trying to come up with a solution to matching. If we are checking for alpha equivalence, then we just check this. And if we are trying to solve a matching problem, then after we run the core algorithm, we need to look, is there another occurrence of x here? So we have x equal t, but there might be some other x inside the rest problem. So if I have x equals s here, then I need to do one more step because I need to check the relation between s and t. So if x needs to be at the same time s and t, we need s and t to be alpha equivalent. So in this case, we need to call again the algorithm. So we don't stop just there. We say the solution will be equals t or x equals s, provided that s and t are alpha equivalent. And here we need to call the algorithm again to simplify this part. So after that, either it's a failure or we can now put a substitution, and it will be a substitution at that point because we can't have several occurrences of x. They are eliminated here, and a freshness context. So we can prove that the solutions are preserved. observed. So what we come up with is really the most general solution. And just an observation, if variables are linear, so you can't have two occurrences of x here, then obviously this phase is irrelevant. You're not going to need this rule, so you can just stop after running the core algorithm. But what I was saying before is that we are interested in making sure that these algorithms run efficiently. So the key points here were trying to avoid potentially several passes over the same tree. We want to do it in one pass. And for that, not only we need to avoid passing, so we do this by using lazy permutations and checking lazily the freshness constraints, so waiting until we are the leaves of the tree. But also we need to have a way of implementing efficiently the permutations. So we can do this, for example, using mutable arrays, if we are implementing this in a functional language like Camel. What we obtain in the end is if the algorithm is just doing alpha equivalence check, I will give you a table with all the complexities, but we get a linear algorithm for alpha equivalence and for matching in the case, the standard case, which is you have a term and you have a ground expression. Okay, so like the matching you need to do in a functional programming language. You will have a ground term and you need to see which of the rules you can apply. So you are matching a rule that has variable with a ground expression. In that case, our algorithm is linear. However, if you are dealing with a term that can contain variables itself and could even be a nonlinear problem, then you need to take into account that there's a second call here for the algorithm. So that's why the complexity is quadratic in that case. But the standard case, which is what we need, for example, to add management of binders and alpha equivalence in a functional language or in a rewriting system, will be the case where we have a rule with variables and a ground term, in which case the complexity is linear. So let me see if the table comes here. Yes. So this slide just summarizes what I gave you. And one of the papers I listed at the beginning, which it says something like alpha equivalence and matching checks, will detail. So if you want to know the details of all this algorithm, exactly how it is implemented, we discussed two different implementations, one using mutable data structures and one in Haskell. And we show why all the different cases give different complexities. But the interesting thing is it's linear for the standard cases. Now, if you move to the non-ground and non-linear matching, which, as I say, this is not something you will need to implement functional programming, but you might just want it for the general case of rewriting terms that have variables and non-linear variables. Why is that quadratic, and could it be done in a better way? So our conjecture, although it's not proved, is that it can be done less than quadratic. But when you do these kind of complexities, you always need to be very careful when you read the complexity of an algorithm, because it is done with respect to the size of the input. So if you say that an algorithm is linear, you are saying it's linear on the size of the input. Now, if you change the way the input is presented, then an algorithm that was maybe quadratic could become linear just because you write your input in a quadratic way. So what I'm trying to say now is the reason why it is quadratic is because we are dealing with these extra things that you don't have in the first order case, the permutations in particular, and the fact that the permutations grow. However, you could start with a representation of your input problem that already has expanded lists of permutations attached everywhere. Okay, so each time you have a variable, you attach, for every atom that is mentioned in the problem, attach an identity permutation with all the swappings A to A, B to B. It's useless, of course, but that makes your problem be bigger, in which case the complexity with respect to the input becomes linear. Now you could say this is a bit like cheating, because why am I going to do that? However, if you think about what I told you at the very beginning of the different alternatives we have to deal with these issues of binding, if you think about the higher order abstract syntax version, where your variables are thought of as functions, and each time you have a variable, let's see, so each time you would have a variable in your problem, you need to write x and then apply it to a list of atoms. All the atoms that could appear in x need to be listed there. Now, the size of your problem automatically is growing, because each variable now, instead of size 1, has size n. And so your algorithm that was quadratic now becomes linear. Okay, so this is why I was saying each time you look at tables like this that tell you nominal matching is linear or nominal matching is quadratic, then yes, there is this difference in the size of the input. And there is a question on the chat: what is the complexity of producing the alternative initial representation? Of course, there's no magic here. So to produce the expanded thing, you will have there the complexity. All I'm saying is, if you're comparing an algorithm that runs linearly on the equivalent problem written in higher order abstract syntax, so running linearly in the equivalent problems written in higher order abstract syntax corresponds to running in quadratic time on the nominal representation. That's what I'm trying to say. The nominal representation is much more compressed with respect to the higher order abstract syntax version. So you can't really compare directly the running time with respect to the input. Okay, you need to somehow take a standard there. And what I was saying is that the nominal syntax being so much more, I don't know, the word is not compressed, because it's just the way it is that when you write a variable, you don't need to write the list of atoms that potentially could appear in an instance. So that makes a difference on the size of the problem you start with. So that was all I wanted to say. So this is why we have the conjecture that it is probably the least possible. You can't get it better than quadratic, because if you could, then the thought would be then you have something less than linear in higher order abstract syntax, which wouldn't seem possible. Okay, so moving on. Oh, this is just this is taken from the paper I was telling you that Christophe Calvez implemented this and ran some tests to compare the algorithms and kind of to see that it was really linear. So you can see here the running times as the size of the input grows. But there's one thing also that I mentioned before so at the end of the lecture in the morning, which was that now we are focusing on nominal matching or alpha equivalence checking. So we have two nominal terms and we want to compare them or we want to match them. But if you are going to implement this in a programming language or a rewriting language, we need a little bit more than nominal matching, because nominal matching just takes a left-hand side and a term and tries to match them. But we said before that our rules are equivariant. So when we write a rule, it represents a family of rules where we could change the names of the atoms. So how do we deal with that at the level of the matching? Well, unfortunately, how we deal with that is that we need to consider not just the rule we wrote, but all the possible equivariant versions. So we need an algorithm of matching more powerful than the one I just mentioned. We need something called equivariant matching, and that is not linear. That's actually, there's a paper by James Cheney that studies this kind of matching problem and shows that it's NP. So, okay, that's not so good, but do we really need this equivariant matching? Could we just deal with nominal matching, so matching modulo alpha equivalence? And remember, I gave you an example and I told you, because somebody was asking me, do we really need equivariance of the rules? And I said, well, if your rule is f of a rewrites to a, nominal matching will only match f of a with f of a. There's no abstraction there. There's nowhere I can apply alpha. So I just need to be aware that if my rule says f of a, there is another version of the rule that says f of b. So when I'm matching, I need to know which rule. And there's no way of avoiding it, except if I avoid rules of that kind. So if I avoid rules that have free atoms, then I don't need to worry about the equivariant matching, because if all the atoms are abstracted, I just need to do matching modulo alpha, and that's what I've shown you before. So that's nominal matching, and that's linear. So can we then just work with rules where all the atoms are abstracted? So what we call closed rules. It's not exactly that. So intuitively, it's that there are no atoms, but the way that you formally write it is a little bit more subtle. But anyway, can we restrict ourselves to just that class of rules and then work with nominal matching, which is very efficient? And the answer is yes. The class of rules that are what we call closed are actually equivalent or as expressive as the class of rules of higher order rewriting systems. So remember at the very beginning, I told you systems like combinatory reduction systems or higher order rewrite systems that use the lambda calculus as a meta language and work modulo alpha in a restricted version of beta to make sure that things are decidable. So those systems, any rule you can write in those systems turns out to be a nominal closed rule. So a rule without free atoms, in which case the nominal matching is sufficient. So that's why it is interesting to work this class of closed rules, which I haven't yet formally defined, but so we want to work with closed rules because they are as expressive as the higher order abstract syntax rules. And they have a very efficient nominal matching algorithm, which does not require equivariant matching. So what is a closed rule? The intuition is that your rule is closed if it doesn't contain free atoms, but it's slightly more complicated than that because the rule could have variables. Obviously, you will have variables in it. So if there are variables, you need to be a bit more precise about what closedness is. It turns out that a rule is closed if it matches with a renamed version of the rule. So this complicated definition here, all it's saying is that you take a rule, you create a version of the rule where you rename all the atoms. So you take new versions of all the atoms and variables while you're at it. So you just create a new copy of your rule and try to match it with the version originally you had, assuming all the names you created are fresh. If you manage to match that new version of the rule with all new names against the old one, it means your rule was closed. So in the example I gave you before, if my rule says f of a rewrites to a, if I create a new copy, let's say f of b rewrites to b, and now I try to match f of b rewrites to b and f of a rewrites to a, that will fail because a and b are different atoms. So that shows my rule wasn't closed. Okay. So this is like an operational test to know if a term is closed. Rename all the atoms with new names, generate new names, rename all the atoms and the variables with new names, and try to match with the original one and see if that succeeds or not. So closed rewriting is actually rewriting with these renamed versions of rules. As I say, it means that we are restricting the language, so we can't write g of a goes to a. This rule is not closed. this one I explained already. It has A free. The test I gave you, which is pick a new version of the rule, let's say with B, and try to match with this one, fails. But this one also is not closed. This is a little bit more subtle, because although you don't see there a free atom directly in the rule, when you think about what this rule is saying that each time I have something of this form, so any instance of this term, I will rewrite to X. Now, one of the rewrites I can do with this rule is a term of the form abstract A in A. I can rewrite it to just A. So an atom that was bound here, I was working with an alpha equivalence class of terms of the form abstract A in A, now becomes just A. And therefore this is not right. It's not a closed rule. Okay. So this is what I was saying, that in practice it's a little bit more subtle than just looking for free atoms. So this version of the rule I gave you, this one is safe, because although we are deleting here in this rewrite step, deleting the abstraction construct, we are putting this condition that A is fresh for X. So A cannot occur in an instance of X. So there is no danger here in removing the abstraction. Okay. Maybe I should now stop a little bit and see if you have any questions. Are there any questions so far? No? Yes?
I have a question. Please.
Yes, sure.
When would I want to use a non-closed rule? So where do they come up in practice?
Well, yes, they don't really come up very often in practice. As I said before, if you were used to higher order abstract syntax, you wouldn't write them because they are impossible to write in that kind of syntax. You could sometimes. So for example, there are some rules in the PyCalculus where you want to remove binders. It's rare. It's not often that you want to remove a binder and look at the actual atom you were using, because this is really what this rule is doing. It's saying I have A bound here. I actually want to see which atom I had, which is bizarre, because if I had an alpha equivalence class, why would I want to do that? But in nominal syntax, you can write it. One case perhaps where people naturally would use a non-closed rule is actually, yes, there is an example for the substitution in the lambda calculus. The rules I gave, and this is an exercise I was going to give you later, but I'll tell you now already. The rules I gave you are closed, these rules. But here maybe you could naturally write a non-closed rule. So, so here I wrote a rule to substitute A for Y in the atom A. This one is closed because remember this is sugar. This sugar is substitute abstraction of A in A with Y. So, but what if instead of saying anything that doesn't contain A, the substitution leaves it alone, I could, instead of Y here, put B. If you put here B, if you say my cases are atom A with A, atom B with A, application F and lambda, then this rule would be non-closed. Okay, but so some people maybe naturally write that, but it's not necessary, and actually it's much better if you say in any term that doesn't contain the atom A, the substitution for the atom A leaves the term alone. I see that Jamie also had, I don't know, Jamie, did you want to say something? Yes.
Can you hear me?
Yes.
Can you hear me? Oh, marvelous. Okay. So with reference to this question about non-closed rules, I can make two suggestions, if that's all right. One is if to some extent, the apparent irrelevance of non-closed rules to some extent is an artifact of how simple this system is. If we have other equations floating around, then we might have situations where we want to release a fresh atom, perhaps because semantically we know that that fresh atom won't matter. So formally we are releasing a fresh atom into the term, but we know that our other equations are going to eliminate it and clean it out. That's a fairly common schema in programming, where you generate a fresh atom because you know that by the end of the computation that atom is not going to matter. And another idea is just to think of, if you think of abstract A in X goes to X, instead of thinking of it as a rewrite, which it is of course, but instead imagine it as some kind of dynamic environment, then dynamically we have created a fresh reference or memory cell or whatever. So these are all examples of natural non-closed behavior. They're not relevant directly here, but they do appear if you reframe the question. I hope that was clear.
Thank you, Jamie. So yeah, so summarizing, you have the power of actually looking under the abstraction here, because atoms in nominal syntax are class objects. So you can deal with rules that have free atoms in them, which, as I said, other systems will not allow you to do that. So it has quite a lot of expressive power, but for most of the time, you don't really need to use that power. So most of the time, closed rules are enough, and closed rules, which come, as I said, almost naturally in most applications, have very good computational properties. So not only they have a very efficient matching, same complexity as the first order matching, but with the advantage that you can match modulo alpha. Also, the other advantage is that they are actually quite easy to understand, because the fact that they don't have these free atoms mean that you don't need to worry about how the atoms are manipulated and treated in your language. Maybe it's a good point now to have a little break. I already told you that the rules I gave you for the substitution in the lambda calculus are closed. I already told you why, but maybe it was too much to check on the fly. So if you want, we are going to have a little break here, just a 5-minute break. If you want, you can think a little bit more about the notion of closed rules before we move on to the next part. So here are the substitutions for the rules for the substitution that I mentioned, and the key one that could be non-closed if you are not careful would be these two here. So the way we set up things, they are closed because we write our substitution with an abstraction here. But if you are not careful, you might want to implement substitution by deleting this abstraction and starting working with the raw terms. So that's the thing to be aware of. When you are using nominal terms, you can work with raw atoms, or you can work with your closed terms, keep everything safely abstracted when you deal with atoms, and computationally it's more efficient. But if you do require the extra power, you have it there. So I'm going to leave you now for 5 minutes. Think about those things. And when we come back, discuss a couple more properties of closed rewriting, because not only is efficient, but it has also good properties, very similar to first order terms. And then we are going to try, if we have time, try to discuss a little bit properties like confluence that are important for this kind of systems. And I think probably that will be that for this afternoon. Okay, if we have time, we can maybe even look at types. So see you again in 5 minutes. Okay. Okay, welcome back. I was just looking at the chat. I saw there was a question about using non-closed rules, and Jamie provided an answer, so many thanks. Before we continue, are there any other questions? So just to recap, so we defined nominal matching, so matching modulo alpha equivalence. We said this takes into account alpha equivalence, but not equivariance. Equivariant nominal matching is exponential. But for big classes of rules, in particular, all the classes of rules that one can write using higher order abstract syntax, the equivalent rules in nominal syntax are closed. So for this big class of rules, nominal matching is sufficient. We don't need equivariant matching. But it is possible to write non-closed rules if we want for some applications. So in particular, when there is some kind of dynamic element, when we want to mention free atoms for some reason, as Jamie was explaining in his answer to in the chat. So we can use them. But if we work with non-closed rules, then we need the equivariant matching. If we work with closed rules, just nominal matching is sufficiently. And closed rules have also very good properties in terms of the rewriting relation. The rewriting relation is uniformly defined on alpha equivalence classes of terms. And so I mentioned those 2 points, but this point about confluence conditions. So when you write a set of rewrite rules to define the semantics of an operator, so I mentioned, for example, at the very beginning that we might want to define the semantics of a let construct, or we might want to define how the beta rule works, or we might want to define some function that operates on first order logic formulas to produce some kind of transformation on them. So when we are doing those sorts of definitions, confluence properties are important, because if what we are trying to define semantically is some kind of functional operator, some functional transformation, we would like that the rules we define for that function have the confluence property. The confluence property ensures unicity of the results, unicity of normal forms. So it's a really interesting property of rewriting. And there's a lot of work in rewriting theory trying to find conditions to make sure that the rules we define are confluent. Checking for confluence in general with arbitrary classes of first order rules is undecidable. That's why it's really important to characterize classes of rules that are confluent, and then we know that if we use those classes of rules, then we are safe. And the good thing with the nominal rewriting with the closed rules is that all that work that has been done to characterize, to define sufficient conditions for confluence of first order rewriting can be applied almost directly to closed nominal rules. So this slide is a bit technical, but as I told you at the very beginning, what I would like with these lectures is to give you the ideas. And then if you are interested on the technical side, then you can check the papers, in particular for this part on rewriting, the paper on nominal rewriting that I pointed out at in the second slide or third slide. You can find all the details for this. But just to give you the ideas, when you are trying to check confluence of a rewrite system, the crucial point is to check for superpositions between left-hand sides of the rules. So to check for confluence, it's important to check for these things called critical pairs. And a critical pair is the result of a superposition between two rules, or more precisely between two copies of rules, because a rule could superpose with itself, okay? So if in your rewrite system you have rules that superpose, there is a danger that you might lose the confluence property. So in that case, what you do, if there are superpositions, is you check what the outcomes are, and you build this thing called the critical pair, which is what you would obtain if you apply one rule and what you would obtain if you apply the other rule, and you compare them. If your critical pairs are joinable, then your system is locally confluent. And local confluence is already quite good, because if your system is locally confluent and also terminates, then that's sufficient for confluence. So finding critical pairs, it's is an important technique to check for confluence, and there are sufficient conditions for confluence. For example, is to have a terminating system without these critical pairs. And how do you check for critical pairs? Well, you need to check for superpositions between rules, and superpositions between rules are created when there are unification between, when there's a unification between a left-hand side of a rule and a part of another left-hand side. So here we see again why it's useful that unification is decidable in nominal terms. For example, this permits to easily check for conditions like confluence, whereas if you were using a format of rules like in higher order abstract syntax that I mentioned at the beginning, where the language is modulo alpha and beta, then trying to unify left-hand sides of rules becomes problematic, because I told you unification modulo beta is undecidable. And although you can restrict the format of the terms of the rules to being within safe fragments of the higher order abstract syntax, fragments that we know have decidable matching or decidable unification, the issue is that once you detect a critical pair, the way to make sure that your system becomes confluent is, if the critical pair is not joinable, then you need to add a rule to join the two terms that form the critical pair. And it's not guaranteed that these new rules that you need to add will be within the safe fragment of the higher order abstract syntax. Whereas if you are using the nominal version of the system, if you are using nominal syntax, nominal rewriting, then there is no problem. If you have a critical pair in your system and it's not joinable, so you don't have enough rules to join it, to make the system confluent, you just add more rules. And you can always add more rules in your system, because we don't have to restrict to decidable unification. It's decidable for the whole language. So that's the idea, is that not only you have an efficient rewriting relation, but also a rewriting relation where you can apply the usual techniques, for example, to check for confluence, to check critical pairs. I'm not going to go into the details of how you find the overlaps, but it's just the usual technique. The only thing is that always being careful that we are dealing with rules with atoms. So in particular, if your rules are not closed, you need to be careful when you are looking at superpositions. Okay, some things that seem obvious in first order syntax might not be obvious when you are using non-closed rules. But if your rules are closed, even that is easy. So we have results that if every critical pair in a closed system is joinable, then the system is locally confluent. And for closed systems, finding critical pairs is relatively easy, because in closed systems you don't need to worry about equivariance and about all the possible versions of rules. So that makes the system work well. If your system is not closed, there are other classes of rules for which this can work too. We call them uniform rules. They are rules that do not generate new atoms. So they might not be closed, but they don't generate new atoms. So the one I mentioned, f of a rewrites to a, is not closed, but it doesn't generate new atoms. We can still work with those. So there's still hope. If you are using non-closed rules, for example, for one of these applications that was mentioned in the chat in Jamie's answer, if you dynamically want to manipulate atoms, as long as you are within the uniform fragment, you don't generate new atoms, you can still work with non-closed rules and easily check properties like confluence. But when your rules are also uniform, then things become much more complicated. So closed rules are alpha stable. Alpha stable means they work uniformly with alpha equivalence classes, and as long as you have this property, your rewriting relation will behave in the expected way, let's say. Now, if you have a rule like f of a, for example, rewrites to b, that's not alpha stable, it's not closed, it's not uniform. You can write it because in the nominal syntax you are allowed to write those things, but you need to be aware that it might be much harder to work with that kind of rewrite relation. So if possible, if you can specify your function using rules that are closed, great. If they are not closed but they are uniform, it's still more or less okay. But if not, just be aware that it might have more complicated behavior. While you are using closed rules, not only the matching is efficient, but also all the techniques you need to apply, for example, for detecting critical pairs, are much simpler, because with closed rules, you can generate the critical pairs just by creating fresh copies of the rules. If the rules are not closed, you need to also create critical pairs modulo equivariance. So that's something else to take into account. I can point you to the papers, as I said, where these things are discussed in detail. If that is something you need to deal with, then look at the technical definitions in the paper. So we have a critical pair lemma for closed rewriting, which is the same lemma as for first order rewriting. So for those of you that are familiar with first order rewriting, it's the same critical pair lemma that says that if all the critical pairs are joinable, then the rewrite relation is locally confluent. And when I say all the critical pairs, if your system is closed, it's sufficient to look at the fresh critical pairs. Fresh critical pairs means that you just take a fresh copy of each rule and you check for superpositions between left-hand sides, and that's enough. You don't need to worry about potentially looking at other versions of the rules with other names. It's an efficient way also to check for confluence, for local confluence. As an application of this effective way of checking local confluence, we can show that the explicit substitution rules that I gave you for the lambda calculus are locally confluent. I told you that they are closed, and there the critical pairs are all joinable. So for that system, we are okay. The substitution is locally confluent, so it's really like a function definition. If you also add beta, and you consider beta plus all the explicit substitution rules, there is a critical pair which is not joinable, because the beta rule superposes with the rule that applies a substitution in an application, and that critical pair is not joinable. So if we wanted to join it, you need to add rules. And this, for those of you that are familiar with explicit substitution systems, it's because here we are really looking at the confluence of the language, confluence for the whole set of terms, even terms with variables. If we only are interested in confluence on the lambda calculus terms, which are the ground terms in our system, then it's easier, okay? But when I say here confluence of the system, I mean confluence for the whole set of terms. So the beta rule plus the explicit substitution rules that I gave is not confluent over the whole set of terms with variables, but again, that's sometimes in systems with explicit substitutions, this is called meta-confluence property. And it's well known that meta-confluence and confluence for the lambda calculus is not the same. You see, when people talk about confluence of the lambda calculus, that would, in our system, would mean ground confluence, because the lambda calculus terms don't have these unknown parts of terms, so they are ground. So ground confluence is easier to prove than meta confluence in the explicit substitution systems. Okay, so moving on. if you're interested in this part, you can try to check these things I just told you. Check that the critical pairs for the part that defines the explicit substitution are joinable, and check also what happens when you add the beta rule. And if you want, tomorrow we can talk more about that. There is another condition that I wanted to briefly mention regarding confluence. So in rewriting systems, the main techniques to prove confluence, one is to check for critical pairs and prove that the critical pairs are joinable. That defines a locally confluent system, which together with termination implies confluence. The other popular technique to prove confluence is to check for orthogonality. And orthogonality means two things. It means your rules are left linear and without overlaps, so no critical pairs. This is a condition that is used, for example, in functional programs. Functional programs require the function definitions to be left linear, so you cannot use the same variable twice in a case, in a matching case, and no overlaps. Okay, so by definition, usually the cases are disjoint; they are checked one after the other. So that ensures confluence in first order systems. It is the case also that a similar property ensures confluence for nominal rewriting systems. So if you have an orthogonal uniform system, so a system that doesn't generate new atoms, then orthogonality and uniformity implies confluence. But you can relax also this condition if your system is closed. So there's something called a quasi-orthogonality, which it doesn't require to check all the overlaps in all the rules. You can just generate new copies of your rules with new fresh names and only check overlaps there. So this is what I mentioned before, the fresh critical pairs. And if your rules are left linear and there is no critical pair in this computed in this way with fresh rules, then if your system is closed, it will be confluent too. So rules that I gave you in an example at the beginning, where I was telling you how to simplify first order logic formulas to get pre-next normal form, you can, for example, check this there because those rules were closed. So for those rules that were closed, being orthogonal in this way, so left linear and no superpositions computed with fresh versions of the rules, guarantees confluence. So this is for those of you who are interested in confluence and have seen techniques to prove confluence in first order systems. Now, confluence is a very, very wide area, and there's a lot of work on it, and there are many other characterizations of fragments of rewriting systems that are orthogonal. These are the two main ones, searching for joinability of critical pairs with termination, or searching for systems that are orthogonal. But there's a lot of references that I could give you here. There are even conferences dedicated to investigating conditions for confluence. There are competition, there are tools that have been implemented to check confluence of systems, and there are competitions there, like for termination, by the way. There are also tools that try to check for termination. Being undecidable properties, both termination and confluence, it means that all we can do is to characterize classes, so to give sufficient conditions. But what is interesting is that these sufficient conditions that are known to work well with first order systems also work well with the closed systems. They are directly applicable. And with non-closed systems, well, with some more work, we can derive also conditions for nominals. And the other thing, yes, I mentioned already that the nominal unification algorithm plays a big role in these techniques, because finding superpositions means using unification to check if two left-hand sides of rules unify. So if you're working with closed rules, there's also an advantage there in having an efficient nominal unification algorithm. Okay, so the next topic is types, looking at typed nominal languages. So before we start this, I want to give you an opportunity to ask questions. Are there any questions so far about the nominal syntax, matching, unification, rewriting, notions of close rewriting? Any questions? Okay, so I know this is a lot of definitions, a lot of notions that you need to get all at once, and quite technical, some of them. So if you need more time to process things and you have some questions later on, what I will do tomorrow when we start, I will again give you another opportunity to ask questions, and we can go back to the things we saw today if you want to go over, if you want me to go over these definitions again. But if there are no questions now, I propose that we start with the topic of typed nominal syntax, and at least for the introduction, and then tomorrow we complete. We won't be able to do the types in 15 minutes, but we can at least start. And then tomorrow my plan would be to complete typed languages and then discuss a little bit reasoning on nominal syntax modulo properties of the operators. So the equational reasoning with, for example, associativity and commutativity operators. But that will be for tomorrow. For today, what I wanted to discuss is, until now, each time we wrote terms, we talked about terms that were untyped. We didn't mention even sorting systems for those terms. So if you look at the paper on nominal unification that I recommended, is one of the first papers I mentioned in the list of further reading, there the nominal syntax actually is typed with a simple system of sorts. So you have a many sorted syntax. So if we want to add types to these terms, we could actually use the techniques that are already known and either put a system with sorts. We could even put types of the kind that we have in the lambda calculus. So either a church style simply typed system where we decorate everything with types, or a curry style, which means that the syntax doesn't include the types, but we have an inference system to assign types to terms. We could even define a language where the types are polymorphic. This is the one I'm going to discuss next. But there are also other versions of typed nominal syntax. For example, there is a version with intersection types, which, again, if you are familiar with the type system for the lambda calculus, you might have seen these intersection type systems, which were again introduced on the 1980s with the goal of studying normalization properties and semantic properties, creating models of the lambda calculus. So intersection types are quite interesting. And these same techniques apply also to nominal terms, have been extended for nominal terms. And I don't know if I put the reference in the further reading list, but if you're interested, I can give you a pointer to that. And finally, there are also systems for nominal syntax with dependent types, which, again, this you might have seen already in systems for the lambda calculus. Dependently typed systems allow you to use terms within the types, so the syntax of types and terms is given together. and there are dependently typed systems for nominal languages. But here in this course, we are just going to focus on the systems with curry types. So a polymorphic curry style type system for nominal terms. So to define that, the idea is to provide, so in addition to what I told you about the terms, we are going to provide a language of types, which we define separately. So the advantage of the curry style is that I don't need to give you again a syntax for nominal terms. We can just keep the syntax of nominal terms I gave you in the first slides and just add the types on top of that. So separately we define the types, and then what we need to do is to have a type assignment system, a system that given a term tries to find a type for that term. So what are the types that we can use for nominal terms? Well, we are going to use data types because remember we are dealing with terms. So terms are structures like trees that can have components or operators, constants of type nat or bool or any type, any user-defined type that we want. The system we are going to define is polymorphic, so we will include variables in the type language. The variables are called alpha, beta, gamma, etc. And to define to get user-defined types, we will permit also in our language of types to use type constructors. Like we have the term formers in the syntax of terms, the F and G, etc., that build terms, we can have a list constructor or a tree constructor and use those to build terms. So this is the grammar for the terms. The only thing that maybe you haven't seen in type systems for first order languages or functional languages is this kind of construction, which is what we call an abstraction type. And we will use these abstraction types to type abstractions. So this will be used when we have a term, an abstraction term, and we will type the atom with type sigma and the term with type tau. So you will see that when I give you the rules for assigning types to terms. So, yes, is there a question?
Yes. So I see we have type variables, but those are not nominal, or are those also nominal?
No, I'm defining a completely separate language for the types. So I have the language of the nominal terms, and now I'm defining a language of types, and I happen to define it just with a syntax that mentions variables, but these type variables are completely separate. So I'm not now using nominal variables here. We could also create a nominal language for types, but this is just a standard type language with constant types, base types like nat, bool, etc., variables like alpha, beta, etc., and type constructors, tuples, product types, and this thing to denote an abstraction. So yeah, they are not specifically nominal, they are just normal types, these ones. The thing though is that we are allowing this language to be tailored to different applications. So we are not working with a fixed set of types. We are permitting to create new types. So this is why we have these type constructors. And we will permit the users or the programmers can say, for example, they can say that this term former successor has this type. It means it constructs, it's a term former, it will construct a term. It will construct a term of type nat if we give it a term of type nat. This length, for example, we can say it's a term constructor that will work on lists, and given a term of type list alpha, it will produce a nat, and this one is polymorphic, so it will work with any term of type list for any alpha. Okay, so here is where we see in the declarations that we have a polymorphic language, and I'm not using a nominal syntax for this. I mean, this is just the standard idea of polymorphic types. So when you're using type variables, it represents a family of types that you can generate by instantiating the variables. Okay? Instantiating the type variables. So we defined the syntax of the nominal terms, the syntax of the types. They are completely separate so far, and actually they will remain separate in this course. There are, as I said, versions of the type system that use dependent types where things are defined at the same time, but here they are completely separate. The thing that we need to now do with a bit of care is the assignment of types to terms. So this is what I said, it's a Cori style system, so our terms don't have type decorations. So the typing rules will have to deal with all the necessary issues to be able to assign a term, to infer a type for the term, taking into account that our terms come with an axiomatization of alpha. So what we would like to do is to create this type system in a way that it works uniformly on alpha equivalence classes. So if we are typing a term and we say that this term has a given type, we would like the type system to make sure that if I give another representative of that equivalence class, I get the same type. So that's why we need to define it a bit carefully, especially if our terms contain free atoms and contain variables that can capture atoms. Remember that a variable in the nominal syntax is just representing an unknown part of the term. So when we type a term that has a variable, we don't know what the substitution for this variable will be. So we will need to make sure that our type system works no matter what comes for this variable. So these are the tricky things that we are going to discuss tomorrow. Again, remember that this is slightly, you see here a type system with more rules maybe than you expect, but it's because we are working with terms with variables. You wouldn't have this if you were working with ground terms, for example. But at the same time, this gives us the possibility of using the type system also to infer types for rules that will have the variables. So I think today we are going to stop here, and tomorrow I'm going to try to go over the typing rules, the properties of the rules, and this system actually has principal types. So I will explain how we find the principal types of the terms, and then hopefully I will have a bit of time left to discuss nominal matching and nominal unification, modulo associativity and commutativity. Is there any question before we stop today? Okay, if you have any questions, you can, I think this will be closed 3:30, but you can still use the Slack channel. I haven't checked it yet, but I will check it later. And otherwise, I think when we meet again tomorrow, we meet on the same link. So it will be tomorrow at 10:30.